Look at this ship for a second. At first glance, Zhu Hai Yun does not look like one of the strangest vessels in China. It is not a giant aircraft carrier. It is not a submarine. It does not even look especially threatening. But that is what makes it unusual, because this ship was not built simply to carry people across the ocean. It was built to carry machines that can leave the ship, spread through the air, across the surface, and below the water, collect data, and then work as a coordinated system. In other words, the real payload of Zhu Hai Yun is not one vehicle. It is an entire network. And that raises a much more interesting question. How do you build a ship whose job is to become the center of a moving robotic fleet? To answer that, we have to start before the drones, before the autonomous navigation, and before the ship ever touched the water. Zhu Hai Yun is 88.5 meters long and 14 meters wide. Its design displacement is around 2,000 tons. Those numbers place it far below the scale of a major warship, but large enough to support a broad working deck, propulsion machinery, survey equipment, communication systems, and the unmanned vehicles it was designed to support. That combination creates the first engineering problem. A normal research ship is designed around laboratories, crew spaces, instruments, storage, and deck work. Zhu Hai Yun needs all of that, but it also needs to act as a base for other vehicles. That changes the priorities of the ship. The deck is not just empty space, it is mission space. The mast is not just a place to mount navigation equipment. It becomes part of a sensor and communications architecture, and the ship itself cannot only move from one waypoint to another. It has to understand its surroundings well enough to navigate with a high degree of autonomy while supporting operations around it. The construction contract was signed in December 2020, and physical construction began in July 2021. From the outside, the early work would still look familiar to almost any modern shipyard. Steel structure first. Hull sections take shape separately before being joined into a continuous vessel. Internal spaces are created long before the final paint, antennas, instruments, and mission equipment make the ship recognizable. This stage matters because everything that comes later depends on geometry that can no longer be casually changed. Deck load paths have to support real equipment. Machinery spaces have to accommodate propulsion and electrical systems. Cable routes, control spaces, sensor interfaces, and service access all have to be planned into a hull that will eventually operate as one integrated machine. And here is the important part. For Zhu Hai Yun, finishing the hull does not finish the ship. It only creates the body. The nervous system comes later. There is another reason this stage is useful visually. Before outfitting, the ship gives us a clean way to show what is structural and what is mission-specific. The hull, decks, bulkheads, machinery foundations, and superstructure create the permanent skeleton. Later systems sit on top of that skeleton and turn empty interfaces into working capability. For a documentary, that separation is valuable because the viewer can literally watch the vessel acquire its identity instead of seeing a completed ship from the beginning. By May 2022, the vessel was ready to be launched at Huangpu Wenchong in Guangzhou. This is the moment shipbuilding can be visually misleading. A newly launched vessel can look almost complete from a distance. The hull exists. The superstructure exists. The ship floats. But many of the systems that define what the vessel can actually do may still be incomplete, uncalibrated, or not yet integrated. And Zhu Hai Yun was especially dependent on that post-launch phase. After launch, the program focused on installation and debugging of core equipment, intelligent systems, and unmanned system support systems. That is where the documentary really changes. Because now, we are no longer just watching a ship being built. We are watching a conventional physical platform being turned into an autonomous one. Think about what that requires. A human navigator can look through a window, interpret another vessel's movement, understand weather, combine radar information with experience, and make a decision. An autonomous ship has to turn those judgments into sensors, software, control logic, communications, and machinery commands. It needs to know where it is. It needs to detect what is around it. It needs to decide whether another vessel is a problem. And then it has to change speed or direction without creating a new problem somewhere else. That is already difficult, and autonomy at sea is not a single switch that gets turned on. Positioning, perception, route planning, collision avoidance, propulsion response, remote supervision, and fault handling all have to agree with one another. A sensor can be working perfectly, and the system can still fail if the software interprets the situation incorrectly. A good decision can still fail if the propulsion system does not execute it properly. The test is therefore not whether one component works, it is whether the chain works. But Zhu Hai Yun adds another layer. It was designed to support dozens of unmanned systems in the air, on the sea surface, and underwater. So the ship is not only a robot, it is a robot designed to work with other robots. This is why the large working deck matters so much. A small unmanned boat, an aerial drone, and an underwater vehicle have completely different handling requirements. One launches into the air. One has to be lowered or released onto the surface. Another may need careful deployment into the water, recovery, charging, maintenance, data transfer, or sensor preparation. The mothership has to support those different machines without becoming a different ship every time the mission changes. That is a modularity problem, and it is one of the most interesting engineering ideas in the whole vessel. Instead of building one enormous platform with every sensor permanently installed on it, the ship can carry smaller systems configured for different jobs. Those machines can spread away from the mothership. They can observe different parts of the environment at the same time, and the ship becomes the common support platform connecting them. This is where the name Mothership stops sounding like marketing and starts making mechanical sense. The ship does not replace the smaller vehicles. It gives them range, power, logistics, communications, and a place to return to. And if you like engineering stories where the strange feature only makes sense after you see the constraint behind it, this is exactly what we look for on Modus Assembly. Because the next problem is even harder. How do you prove that all of this actually works at sea? You cannot validate an autonomous research ship only while it is tied to a dock. The ocean adds motion, weather, traffic, poor visibility, changing sensor conditions, and the constant possibility that something outside the test plan will happen. In November 2022, Zhu Hai Yun received a China Classification Society certificate for open water autonomous navigation. That is a major milestone because it turns the autonomy story from a design intention into something that had to pass an external classification process. But certification is still not the final payoff. Real operation is. The ship was delivered in January 2023. Later that year, it completed a long autonomous research voyage lasting more than 200 hours and covering about 1,500 nautical miles. During that voyage, the vessel encountered real coastal traffic and sea conditions and reportedly completed more than 100 autonomous collision avoidance actions. That may be the single most important reveal in the story. Because the unusual part of Zhu Hai Yun is not that someone drew a futuristic ship and called it autonomous. The unusual part is that the ship went to sea and had to make repeated navigation decisions in the real environment it was designed for. And then the mothership idea began to become visible in operations too. In 2024, the vessel was used alongside other research and test platforms, and in one documented exercise, it served as the support mothership for groups of unmanned surface vessels. Large and medium unmanned boats were used together for coordinated observation. The ship supported the formation, control, and data collection task. That is the concept moving from architecture to behavior. One ship arrives in an operating area. Then smaller vehicles spread outward. Instead of forcing the mothership itself to physically occupy every measurement point, the network expands around it. That is why a vessel like this can matter far beyond its size. Not because the hull is enormous, because the hull becomes the center of a much larger sensing footprint. And this is also where the dual-use discussion has to be handled carefully. Zhu Hai Yun is officially a scientific research vessel. Its documented missions include ocean observation, surveying, environmental work, testing, and coordinated unmanned research. Those are the facts. But the underlying technologies are also strategically relevant. Autonomous navigation, remote control, distributed sensing, unmanned surface craft, underwater systems, and networked maritime operations do not become irrelevant simply because the mission is civilian. The correct way to understand Zhu Hai Yun is not to secretly turn it into a warship. It is to recognize that the same industrial capabilities that make advanced ocean science possible can also matter to any country trying to understand and operate across large maritime areas. That distinction is important, and visually, it gives us a much better documentary. We do not need to invent missile launchers, weapons, or fictional combat missions to make this ship interesting. The real machine is already strange enough. An 88.5-meter research vessel is built in a conventional shipyard. Its hull is assembled like a ship. It is launched like a ship. Then, after launch, it receives the systems that change what the ship actually is. Sensors, autonomy, remote control, mission support equipment, interfaces for unmanned vehicles. Then those systems are tested together. The ship is certified. It is delivered. And finally, it goes to sea, where the engineering has to survive outside the factory. That is the full answer to the question we started with. Why build a ship whose real payload is a network? Because one large vessel cannot be everywhere at once. But a mothership carrying smaller autonomous systems can arrive with its own mobile fleet, deploy those systems into different parts of the air and ocean, support them, coordinate them, and bring the whole operation back together around one platform. The hull gives the system endurance. The deck gives it flexibility. The communications architecture connects it. And autonomy allows the mothership itself to become part of the network instead of merely carrying it. That is what makes Zhu Hai Yun unusual. It looks like one ship. But the engineering was designed around the idea that one ship is not enough. And once you understand that, the strange layout, the broad working deck, the autonomous navigation, and the fleets of smaller machines all become parts of the same design. A ship built not just to travel across the ocean, but to arrive, open up, and turn the ocean around it into a connected field of machines. Subscribe to Modus Assembly for more engineering stories where the strangest machines make sense only after you see how they are built.